Our first step is to run the dataset on ArcGIS Pro, which is the leading GIS software in the market, and we'll use this software to process the LiDAR imagery to extract the building footprint. The area of interest for us is a neighborhood in Copenhagen, the capital of Denmark. The name of the area is called Tuborg. And from this TIFF image, which is open on your screen, it shows us the extent of the neighborhood just for our reference purposes. You can see that it's an urban neighborhood with buildings, with parks, with roads, and with a water body on its east. In the dataset, there are 2 LiDAR files which are available. As a next step, what we will do is we'll merge these 2 LiDAR files so that the processing can happen seamlessly. Next, we'll proceed to add those 2 LiDAR files called LAS, which is a short for laser file, because LiDAR is called interchangeably as laser files as well. There are 5 million and 3 million data points within each of the LiDAR datasets respectively. The points are separated by a margin of 0.3 meters on an average. It is a very dense dataset. One of the reasons why LiDAR is so often used, because it creates a very vivid 3-dimensional representation of the area under observation. A sum total of 8 million points are there. And we can see that they have not been classified yet, as in they are unassigned at the moment. The coordinate system is ETRS 1989 UTM zone 32N. As a next step, the merged LiDAR dataset will be loaded onto the map. It creates a very colorful, vivid representation of the area under observation. The values are color coded as per the elevation. So areas under high elevation are typically yellow, orange, and red, whereas the ones with lower elevation values are typically light blue and dark blue in color. Because it is a 3-dimensional imagery, we can zoom in, explore the properties, see the point cloud for ourselves before we go on to the next processing step. As a next step, what we will do is basically classify the points. As you had already known, the points have been unassigned so far, which is why the image is currently looking gray. If you see on the left on your screen, that is marked as unassigned. Our next point is to basically classify these points which are at ground level. So we'll use the geoprocessing tool. There is a particular tool which can capture the ground pixels from the LiDAR dataset. We'll run this tool now. We select our dataset. And we'll run this tool. Straight away, the area which are at the ground level are being marked as brown. By navigating the 3D imagery, the difference between both the classes of pixels are clearly visible. We've done this particular step because we want to eliminate the ground pixel points, whereas the other necessity is we'll use these ground pixel points to create a digital elevation model of the surface. The reason why we do this step is because the standard digital elevation model, which is there as part of the base map, is at a very macro level. It is not at the desired accuracy which we need. So our next step is to run the LAS dataset to raster tool, which essentially will be used to convert the points which are classified as ground into a uniform raster layer which contains the elevation value for all the points. We've used a technique called interpolation, as you had known that there is 0.3 meters of gap between the pixels. So our objective was to fill those gaps as well. So using the natural neighbor method, we've classified. The DEM has been created. Areas which are high are brighter in color, whereas the areas which are of low elevation are darker in shade. This forms the framework of our processing. The ground points converted into a DEM. As a next step, we'll see what are the remaining points, because our ultimate objective is to create the building footprint. So is this particular image sufficient to extract building footprint? Not quite. We'll use the classify LAS noise tool because the imagery is not quite appropriate for our requirements yet. Why is it so? Because there are certain features which are taller than a building. For example, a telecom tower or a power line, for example. The first step is to eliminate any errors in the dataset, so any point below the ground level. So we've done the minimum height at -2 meters and run the tool. This is called the low noise. The next step is to identify the high noise, as in typically there are points which are higher than the building. So typically in this neighborhood, the tallest building is 40 meters in size. So we've done the maximum height as 42 meters so as to eliminate any points which could be taller than those buildings. As a result, once the low noise and high noise has been classified, we can see those demarcations in the red color. Now over here, what is this particular red color? These are construction cranes on top of buildings. So this is a kind of a noise which we eliminate from the dataset. There are certain errors, which is the low noise also, which are bordering the coastline as well. So those have been identified as well. All the points are those red points which you see on your image. So initially we've categorized and removed the ground points. Subsequently we've categorized and removed the noise. And so what we are left now are typically your building data points, but that is not all. These could be several other features, for example, vehicles, for example, vegetation, and any other material which is not ground and which is not noise would be classified in this cross-section of the LiDAR imagery. There is a specific tool now which we will be able to run, which is the LAS building tool. We've classified the rooftop height as well as the minimum area of an average building. These two aspects are necessary so that the tool can identify buildings from this particular dataset. Now you may be wondering, if the standalone tool existed, then why not run it in the first place? This is because there is a processing chain, a sequence of actions which we need to do, and performing the ground point classification and then separating it out from the dataset enables this tool to run effectively. The building classification is done basis honing on the LiDAR reflectance properties. So when LiDAR pulse interacts with the building, it basically returns as a single pulse of light to the sensor. Whereas if it interacts with, let's say, leaves of a tree, it returns as multiple diffused pulses. So this particular tool utilizes this particular property of reflectance values to isolate and demarcate buildings. We also have to set the minimum rooftop height as well as a minimum area of a particular building type for this tool to basically isolate the buildings effectively. This is just to clarify that the gray visuals on your screen are the unassigned points, as in these aren't the building, the noise as well as the ground level. The next step is to basically transfer the building points which were extracted onto the 2D version of the map. Initially we were exploring the scene in 3D. Now we will do subsequent processing steps in 2D mode. The red pixels on the screen are the building footprints which have been transferred. When we overlay it on top of the ortho-rectified imagery, you can see more or less the buildings have been clearly identified, although there is a difference in perspective because the ortho-rectified image was captured from a particular angle, whereas the airborne LiDAR imagery was captured from another angle altogether. The next processing step is to basically convert these points into a continuous raster imagery. So we select that particular data set and basically the tool classifies a cluster of points which are buildings into a single cell comprising and classified as a building. So once we've run this tool, we can see that the buildings have been colored in a dark gray tone, and which we'll change so as to make it much more visible. Now it is pink in color. As we explore the raster imagery, you will see that there are certain inconsistencies. For example, there are certain gaps in the buildings. Then the building edges are rough. There are certain small objects which have been classified as buildings, and perhaps these may not be buildings. So to perform these corrective actions, we need to first convert the raster into individual building polygons. Once we've run this tool, a new layer has been created which is currently colored white, but then we will change the color to resemble the pink color, which is much more visible on this particular base map. As a subsequent step, what we will do is examine the attributes. You will see that a sum total of 796 building polygons had been identified when we had run the classify buildings tool. Now, not all of them, as I have told you, are buildings. We need to perform certain corrective actions on the inconsistencies which we had spotted and elaborated earlier. How do we basically perform these corrective actions? So at first, let's say we want to remove certain features such as the one on the road, which is clearly not a building. And how do we basically remove that? It is a very simple technique. We examine the dimensions of the buildings. We see that they have a particular length, they have a particular area on an average, and certain features which are, different and have a clearly, the length of the particular object is below a particular standard or the area is below a particular value. Then we basically use a filter to classify, isolate and remove that particular layer. So currently what we are telling the software to do is, if the area is greater than a particular figure, which is 70 square meters, then basically you categorize it as a building. Otherwise, you do not categorize it as a building. So once we run this tool, the buildings have been classified and overshadowed by the blue border. But then you see the point on the road, there is no blue border on that particular element or a feature. So which means it has not been selected. So essentially what we are doing as a subsequent step is isolating the buildings and therefore removing the small features which are not buildings. The new layer has been created on your left. As a next step, what we will do is regularize the building footprint. Now you may wonder, what is regularization mean? It basically uses certain geometric properties. We set the tolerance, densification and precision values. Without going into the technicalities of it, essentially what we are saying is, if the geometries of a particular feature or a polygon has a tendency to be a building, then please, make it as a smooth edge rather than a very rugged, jagged edge. So once this tool is run, and when we, compare it with the previous output with this new output, you see that the building has been clearly, you can say, I have a very smooth edge, which is normal, right? In terms of the real life, the buildings do not have rough edges. They have a very smooth edges. So this is one type of categorization or corrective measure which we do to make the building footprint even more better. Subsequently, you will see on the left of your screen a small object, for example, has been incorrectly identified as a building. Now, this matches the building minimum area criteria, but it's still not a building. Then what can we do? We can select that particular object and remove it manually. So this is again another type of corrective measure which we can perform. Now over here you see there is an incomplete building wherein the polygon is there, but then it does not reflect the entire building view. It rather, on the left hand side, it is basically not clear. So we can use a modify features tool to basically manually draw the outline, and it's not like you'll have to draw the complete outline by yourself. You just have to select the vertices, and the tool basically automates the entire process and creates a rectangular shaped object. The next step entails creating 3D representations of the building footprint, which is essentially our objective of this exercise. Now for this to happen, we have to migrate once again to the 3D view, and then we have to subsequently run a particular tool known as multipatch. This basically leverages ArcGIS Pro's 3D capabilities to create the buildings in 3D view. We essentially use 3 data points for this. One is the LiDAR points which were classified as buildings initially. The second one is the cleaned up 2D footprint which we had done in the recent past. And the third one is the digital elevation model, which, if you remember, we had basically created this out of the LiDAR points classified as ground very early on in this exercise. So this last building multipatch tool utilizes these 3 data sets to create what would appear on your screen now is the 3D buildings. We colored these buildings in yellow color so as to make it much more visible on the plain white base map. This is the output which we had aspired to create when we had initiated this exercise, and after several processing steps and a few corrective steps, this appears to be a very pleasing and a realistic 3D building output. We'll see the attributes. From roughly 750 plus buildings, we've now basically isolated to 170 buildings in this particular neighborhood of Tuborg in Copenhagen, Denmark. There's one last step which we need to do to make this 3D representation even more clearer. The base map over here utilizes a World 3D digital elevation model, which is by default the 3D view in ArcGIS Pro. Now this is done at a macro level, but then because we have LiDAR dataset and we had created a DEM out of it, we will utilize that as part of the base map's elevation model. Now you may wonder what is the reason behind doing it. It appears very realistic. Actually, no. In a short moment, you will see how changing the digital elevation model to a more realistic version changes the complete attributes of the buildings. So now you see the ground level of the building is much more smoother. Hence, we've used the digital elevation model to create an even more positionally accurate 3D representation of the building footprint. With this, we conclude our exercise.